We'll start with standard enthalpy of formation. And let's start with just what does that mean. So the notation for this is delta H, which is enthalpy. We put a little F next to it to mean formation. That means forming an element from its, or forming a compound from its elements. And this little superscript degree sign, that means standard conditions. Okay, that's what this is down here. So what are standard conditions? Standard conditions are 1 mole of the stuff, whatever it happens to be, 1 atmosphere pressure, and 25 degrees C. Now you might be looking at this and thinking, oh, that's STP. No, it's not. Okay, and why is it not? Because it's actually at 25 degrees C. STP is 1 atmosphere pressure, 0 degrees C. And standard conditions are at 25 degrees C. Why is that? I don't know. That's just the way somebody made a decision. So you might ask yourself, what is it? What does this mean? This is table 6.5 from your book. And you notice there's a whole bunch of elements and or compounds, and you notice there's a bunch of numbers next to them. And if you look at the top of each column, there's a delta H sub F in kilojoules per mole. Okay, so the standard units are kilojoules per mole. So what they've done is someone has gone and experimentally determined how much energy does it take to make a compound at 1 atmosphere pressure and at 25 degrees C. Because delta H is a state function, remember I said something like volume is a state function. It doesn't matter what path you've taken, all that it matters is the initial condition and the final condition, and you can figure out the change in volume. Same thing with temperature. I gave you that example where if I heat something up and cool it down and you walk out of the lab and you haven't seen it, 2 experiments going, one goes directly from 100 to 0, the other one takes some crazy path. At the end of the day, all that matters is the final temperature minus the initial temperature. The change in temperature is all that matters. That's a state function. Delta H is also a state function. So because it doesn't matter how I measured this, as long as I do it at 1 atmosphere pressure, 25 degrees C, I can get a number which tells me something about that material. All right, so before I get into what these numbers mean and interpreting them, let's think about how numbers are generated. Now, some numbers are on what's called an absolute scale. Temperature in Kelvin is a good example of this. Temperature in Kelvin. So there is a 0 point in the temperature scale. That 0 point is called absolute 0. And every temperature that's greater than 0, like 273.15, that's the same thing as 0 degrees C. 373.15, that's the same thing as 100 degrees C. It's actually 100.15 degrees C. This is in Kelvin. Okay, that's the melting point of water. That's the boiling point of water. But because there's this thing that is called absolute 0, we can define a temperature scale that's an absolute temperature scale, and every temperature we measure is relative to absolute 0. Okay, so in other words, we have a baseline, and we can measure everything above that. A lot of measurements we do, though, don't have a baseline scale. They're measured relative to something else. So let me erase this, just so I can use this space right here. And let's get another pen. A lot of things are measured relative to something else. For example, all the elements on the periodic table, you remember, were defined based on some arbitrary mass of 12.0000 atomic mass units for one specific isotope of carbon called carbon-12. So carbon-12 was defined to be 12 AMUs. Now, if you remember the discussion we had months ago, probably 2 months ago, we couldn't actually measure an AMU. But if we make carbon-12, then everything is relative to that. So if helium's 4, it's 3 times lighter than carbon. hydrogen is 1, it's 12 times lighter than carbon, etc. Okay? So the entire periodic table is based on carbon-12 relative to that number. So it's a relative scale based on carbon-12. Could they have made the periodic table based on gold? Sure. They could have absolutely done that. Let me give you another example. Elevations. We have mountains. We have oceans. Oceans have some depth associated with them. And somebody decided we are going to call the baseline elevation measurement sea level. And every measurement we make for anything that's higher than sea level is going to have a positive number, and every measurement we make that's less than sea level is going to have a negative number. So you don't have to be in the sea, like Death Valley is actually a negative number, but all the measurements are made relative to the average ocean height, which we call sea level. Okay? Now you might be saying, well, the waves are higher, and sometimes it's high tide, sometimes it's low tide. That's a complication of this measurement. Okay, but the fact of the matter is somebody decided a long time ago we are going to measure all elevations relative to sea level. Now, could we have taken the peak of Mount Everest and made every single elevation number relative to the peak of Mount Everest? Yes, we could have. Then what would have happened to all the elevations? Well, they'd all be negative. It'd all be some negative value, because if we had Mount Everest as my highest number and everything relative to that, then every elevation value that's reported would be a negative number. Could we have taken the lowest peak in the ocean and measured everything relative to that? Yes, we could have. That would have been a positive number. Now you might already be thinking, well, ocean sands move around and everything, and how do you know it's staying exactly the same? And that's a pretty hard measurement to make, right? The bottom of the ocean, I don't know if it's in the middle of the Atlantic. I think it's in the middle of the Atlantic is the deepest spot. So are you going to go back there and measure it each time? Okay, yeah, those are details. That would be a complicated measurement, and that's a good reason not to do that. But you could have done that. Could you have made elevations relative to the distance from the moon? Yes, you could have done that. Now, granted, that changes its, the orbit isn't a circle, it's an ellipse. So that wouldn't have been an ideal way to do it. So somebody a long time ago said, you know what? Let's make all of these elevations relative to sea level, and no matter where we are, if it's above sea level, it's going to be a positive number. If it's below sea level, it's going to be a negative number. Okay? The enthalpy of formation is the same idea. So let me erase this. Enthalpy of formation is another sea level measurement. And what they've done is they've said, all right, we are going to define the enthalpy of formation for a very specific case. And that specific case is that an element in its most stable form at 25 degrees C and 1 atmosphere pressure we are going to say delta H sub F is equal to 0 kilojoules per mole for that particular element. Okay, so let's take a look over on this table here. Here's oxygen, O2 gas. So O2 is the most stable form of oxygen in the gas state at 25 degrees C. That's going to have a 0. Silver in the solid state is defined to be 0. Sodium in the solid state is defined to be 0. Fluorine is a gas. It's F2. And that one's also defined to be 0. So every single element, whatever it is, in its most stable form, by definition, is 0. Okay, this one happens to have about 10 elements, but if we go to the back of the book, there's an appendix at the back of the book that has all this thermodynamic data. Every single element on the periodic table, in its most stable form, by definition, is going to be 0 kilojoules per mole. That's how the enthalpy of formation is defined. That's how the sea level is defined. All right, so you might be saying, why are you calling that the sea level? Well, let's take another element or another compound. This is O3, ozone. Notice that's a positive number. So every elemental form that's not the most stable form is going to be endothermic relative to the most stable form. Let me say that again. Every pure element relative to whatever its most stable form is going to be a positive number for delta H. So O3 is one example. Here's atomic fluorine. That's just F, gas phase fluorine. That's plus 79. Let's look at over here. Diamond is the most stable form of carbon, or excuse me, graphite. And diamond is also a positive number, plus 1.88. And we could do this for all this. Here's bromine liquid, Br2 liquid. If we just take Br, atomic bromine, that's plus 112 kilojoules per mole. All right. So let me state this again, just so you got it. Whatever an element is in its most stable form, it's defined to be 0. That's how they made sea level. And then any compound or any element relative to that will either be positive, which means it takes energy to make, endothermic, or it's going to be negative relative to that, which means it's exothermic, releases energy relative to that. Every compound on Earth is either positive or negative relative to the element in its most stable form. So we've just looked at a couple combinations where it's the element in its most stable form and it's the element in a not as stable form. So here's solid sodium. Can you make a gas phase sodium? Yes, you got to put some energy in. 107.5 kilojoules per mole, in fact. Okay? So every element can exist in another form, but it's always going to take energy. It's always endothermic to do that, like ozone, like atomic fluorine compared to F2 gas. Okay? That's the first thing we get from this table. The second thing we get is there's a lot of things in here with negative numbers. There's a negative, that's HF. Sodium carbonate is negative 1120. Sodium chloride is negative 411. You notice what all these have in common. These are all compounds. Okay? Negative 634 for calcium oxide, negative 1207 for calcium carbonate. What do all those things have in common? They're all compounds. What that means is when you form a compound, compared to its elements, it's actually more stable. That's the reason why nature forms these compounds, because thermodynamically, they're more favorable. They're exothermic. They like to go into that form. Okay? Now, here's the other thing, which is a little more subtle thing. Let's take this one, H2O gas. Notice that one is minus 241.8. Here's H2O liquid, minus 285.8. So the states of matter matter because the energies are different in the states of matter. Remember in class on Tuesday, I told you, you have to specify the states of matter. If you do not specify the states of matter, you're not going to get full credit on a short answer problem because they're different, right? The energies are actually different, whether it's a gas or whether it's a liquid. Now, this table is showing you, I don't know how many things are on here, 40 or 50 things on here. The back of the book, there's literally hundreds and hundreds. If you go to the CRC Handbook of Chemistry and Physics, there are thousands, tens of thousands of compounds that somebody has taken the time to measure the delta H of formation of that compound. Now, you might be thinking, geez, that's a pretty boring, pretty tedious thing. Yes, it is. Okay, that's the sort of thing some people get their PhDs for. But somebody's taken the time to do that. So a good question you can ask yourself at this point is, why would somebody take their time to do that? And why is somebody going to get a PhD just because they went and measured all these delta H sub F values? Here's the reason why. Because they've done you a massive favor by doing that. And the massive favor they've done is you don't have to do a calorimetry experiment anymore to calculate delta H for some chemical reaction. Any chemical reaction where you can look up these delta H sub F values you don't even need to do a calorimetry experiment anymore. Now, a good question you can ask yourself now is, why do we even do calorimetry experiments? Well, that's how these numbers came from. Okay, somebody had to do that, and they did a calorimetry experiment to get these delta H values. But once you've got them, they're tremendously powerful, because now we can use the fact that delta H is a state function, and we can use the fact that it doesn't matter the conditions that I got to that number. All that it matters is what the number is, and I can go and calculate what delta H is.